the star. We think we know. Every morning, it rises without effort. Every evening, it disappears without explanation. For as long as humanity has existed, it has been there, constant, reliable, and seemingly understood. The sun. It warms our planet, defines our days, and makes life possible. We plan our time around it. We build our civilizations beneath it. We trust it completely. And because of that trust, we rarely question it. The sun feels familiar. Too familiar. When people think about cosmic mysteries, they imagine distant galaxies, invisible black holes, or stars billions of light years away. The universe feels strange only when it feels far. Our closest star does not feel mysterious. It feels ordinary, predictable, safe. But that sense of familiarity may be an illusion. Because despite centuries of observation, decades of satellites, and entire branches of science devoted to studying it, the sun still behaves in ways scientists cannot fully explain. And the closer we look, the more questions emerge. The sun is not just another star in the sky. It is the star, the only one close enough for us to study in detail. The only one that directly affects every aspect of life on Earth. And yet, some of its most fundamental processes remain hidden. What we think we know about the sun comes from models, mathematical descriptions built from physics we understand. These models work well most of the time. They explain why the sun shines, how energy flows outward, and why it has remained stable for billions of years. But most of the time is not the same as completely. Beneath the calm glow of daylight, the sun is a place of violence, of extremes, of constant motion. Its surface is not solid. Its interior is not quiet. Its magnetic fields twist and snap like living things. And occasionally, the sun reminds us that it is not passive. For centuries, the sun was worshipped as a god. Later, it was reduced to a simple nuclear furnace, a predictable engine converting hydrogen into light. That description was comforting. It suggested control. It suggested understanding. But modern observations tell a more complicated story. The sun is not a smooth, steady sphere. Its surface boils. Vast currents of plasma rise and fall. Dark regions appear and vanish. Enormous arcs of glowing matter leap into space and collapse back inward. These events are not rare. They happen constantly. And still, we do not fully understand why. The sun's behavior follows cycles, roughly 11 years long, during which activity increases and decreases. These cycles affect everything from satellite reliability to Earth's upper atmosphere. Scientists can describe the cycle after it happens, but predicting it precisely remains difficult. Sometimes, the sun behaves unexpectedly. Activity drops when it should rise, or surges when models predict calm. These deviations are not dramatic enough to alarm the public, but they are significant enough to trouble scientists. Because the sun should not surprise us this way. It is our closest star. We have sent spacecraft to orbit it. We have instruments that monitor it constantly. And yet, when it comes to forecasting its behavior with confidence, uncertainty remains. One of the reasons is that the sun is not just a ball of burning gas. It is plasma, matter so energized that electrons and nuclei move freely. Plasma behaves differently than solids, liquids, or gases. It interacts strongly with magnetic fields, creating complexity that resists simple explanation. The sun is dominated by magnetism. Its magnetic field is not fixed or orderly. It twists, tangles, breaks, and reconnects. These magnetic events drive solar flares and eruptions that can release more energy than billions of nuclear bombs combined in seconds. These eruptions are not theoretical. They have been observed, they have reached Earth, and they have caused damage. Yet even with all this data, scientists still struggle to answer a basic question. Why does the sun behave the way it does? The sun's interior is completely inaccessible. No probe can enter it. No signal escapes directly from its core, and everything we know about its inner structure comes from indirect measurements, vibrations, neutrinos, and surface behavior interpreted through models. Those models are impressive. They are based on well-tested physics, but they are still models. And sometimes, observations do not align perfectly with expectations. The sun's core is believed to be stable, steadily fusing hydrogen into helium. This process has powered the sun for billions of years and should continue for billions more. There is no evidence that the sun is about to explode or collapse. But stability does not mean simplicity. Small variations inside the sun can have large effects on its surface and magnetic behavior. Tiny changes in flow patterns, rotation rates, or magnetic field alignment can cascade outward, altering activity across the entire star. The sun rotates, but not as a solid body. Its equator spins faster than its poles. Different layers rotate at different speeds. This differential rotation stretches magnetic field lines until they snap. Why does this rotation behave the way it does? Why do these patterns shift over time? We do not fully know. Even more puzzling is the sun's outer atmosphere, the corona. Logic suggests that the farther you move from a heat source, the cooler it becomes. Yet the sun defies this expectation. Its surface temperature is about 5,500 degrees Celsius. Its corona reaches millions of degrees. This should not happen. Heat should flow outward and dissipate. But the sun's outer atmosphere is somehow hotter than the layers below it. This contradiction has been known for decades, and while several theories exist, none have been confirmed conclusively. This is not a minor detail. It is a fundamental failure of understanding. The sun is not hiding its behavior intentionally. It is simply complex beyond intuition. Its processes operate across enormous ranges of scale, from subatomic particle interactions to flows larger than Earth. Human brains are not built to grasp such systems easily. Because the sun feels close and familiar, we underestimate its complexity. We assume that proximity equals understanding. But in reality, distance is not the barrier. Physics is. The sun sits at an uncomfortable boundary. It is too extreme for direct experimentation, yet too close to ignore. Its behavior affects Earth in subtle ways every day. Solar radiation influences climate. Solar storms threaten technology. Magnetic disturbances ripple through Earth's atmosphere invisibly. Most of the time, nothing happens. And that is what makes the sun dangerous to underestimate. Because rare events matter. History shows that the sun is capable of releasing energy far beyond what modern society is prepared to handle. Evidence preserved in tree rings and ice cores suggests past solar events stronger than anything recorded in the space age. If such an event occurred today, the consequences would be global. And yet, predicting such events remains unreliable. This brings us back to the central question. If the sun is so well studied, why does uncertainty remain? Why does our closest star still surprise us? The answer may be unsettling in its simplicity. We understand the sun well enough to rely on it, but not well enough to be confident. There is a difference between familiarity and mastery, and the sun exists in that gap. It behaves according to physical laws we know, but those laws interact in ways we are still learning to untangle. The sun is not hiding secrets in the sense of conspiracy. It is hiding them in complexity, in layers we cannot see, in interactions too subtle to isolate easily. It is not mysterious because it is strange. It is mysterious because it is ordinary and enormously powerful. As we move deeper into this documentary, we will leave the comfort of daylight assumptions behind. We will explore what scientists know, what they suspect, and what remains unresolved. We will examine the sun's surface, its interior, its magnetic behavior, and its history of surprises. Because the star that feels safest may also be the one we least understand. And understanding it may matter more than understanding any other object in the universe. Why the sun matters more than any other star. Of all the stars in the universe, only one truly matters to us. Not because it is the largest, not because it is the brightest, but because it is close enough to shape everything we are. The sun is not just another object in space. It is the reason Earth is not frozen, the reason water flows, the reason seasons exist, the reason life began at all. Every breath, every ocean current, every ecosystem traces its energy back to a single source. And that is precisely why the sun deserves more scrutiny than any other star. Modern civilization is built on the assumption that the sun will behave tomorrow as it did yesterday. That assumption is woven into agriculture, energy systems, navigation, communication, and climate models. We do not think about it consciously, but our entire technological world depends on solar stability. This dependence is so complete that it has become invisible. For most of human history, the sun was simply there, rising and setting with reassuring regularity. Its warmth was felt, not analyzed. Its light was trusted, not questioned. Even ancient cultures that feared eclipses still believed the sun itself was eternal and reliable. Science replaced worship with equations, but the assumption remained. The sun is stable. The sun is predictable. The sun is understood. But stability is not the same as simplicity. The sun generates more energy every second than humanity has produced in its entire history. This energy is released through nuclear fusion, a process that transforms matter directly into energy. At the sun's core, hydrogen atoms are fused together under immense pressure and temperature, releasing light that takes thousands of years to reach the surface. By the time sunlight touches Earth, it feels gentle. That gentleness is deceptive. The sun's output may appear constant, but it is not perfectly so. Its brightness fluctuates slightly. Its magnetic field evolves. Its activity waxes and wanes. These variations are small on human timescales, but they are not meaningless. Tiny changes in solar radiation can influence Earth's upper atmosphere. They can alter satellite drag, affect radio communications, and change how energy flows through climate systems. Most of these effects are subtle. Some are cumulative. A few are dramatic. The sun does not need to explode to affect us. It only needs to misbehave. Our solar storms, bursts of charged particles and radiation, travel outward from the sun at incredible speeds. When they reach Earth, they interact with our planet's magnetic field. Most of the time, this interaction produces nothing more than auroras. But sometimes, the interaction is violent. Power grids can overload, satellites can fail, GPS signals can degrade, communications can be disrupted across continents. These are not hypothetical scenarios. They have happened before, on smaller scales. The difference today is vulnerability. Modern civilization is wrapped in technology that assumes a calm sun. Electrical infrastructure spans continents. Satellites guide transportation, finance, and defense. Digital systems depend on uninterrupted signals. A solar event that would have been an inconvenience a century ago could now be catastrophic. And yet, our ability to predict such events remains limited. This is not because scientists lack effort or intelligence. It is because the sun is an extraordinarily complex system. It operates at the intersection of nuclear physics, fluid dynamics, electromagnetism, and plasma physics, all under extreme conditions. The sun's interior drives its behavior, but that interior cannot be observed directly. Signals from the core are filtered, altered, and delayed as they move outward. By the time we observe surface effects, the causes may be long past. This creates a problem unique to the sun. We are affected by it more than any other star. Yet, it is one of the hardest to understand completely. Distant stars can be studied statistically. Patterns emerge from large samples. The sun is only one object. We cannot compare it to another sun. We must understand it as an individual. And individuals are always more complex than averages. The sun also exists in a delicate balance. It is massive enough to sustain fusion, but not massive enough to burn uncontrollably. It rotates slowly compared to other stars, but fast enough to generate complex magnetic fields. It is old enough to be stable, but young enough to remain active. This balance is not guaranteed forever. Stars evolve. Over billions of years, the sun will change. It will grow brighter. Its output will increase gradually. These changes are slow, but they are inevitable. Understanding the sun is not just about today. It is about Earth's future. Even now, the sun's influence extends beyond light and heat. Solar wind, a constant stream of charged particles, flows outward, shaping the heliosphere, a vast magnetic bubble that surrounds the solar system. This bubble shields Earth from high-energy cosmic radiation. The sun is not just a source of energy, it is a protector. If solar activity weakens significantly, the heliosphere could shrink. If it intensifies unpredictably, radiation levels could rise. Both scenarios carry consequences. Yet the mechanisms controlling these processes are not fully understood. One reason the sun is difficult to predict is that it is not uniform. Different regions behave differently. The equator rotates faster than the poles. Magnetic activity concentrates in bands that migrate over time. Plasma flows shift direction and speed. These flows interact in nonlinear ways. Small changes can produce large effects. Feedback loops amplify disturbances. Predictability breaks down, and this is why weather forecasts on Earth become unreliable beyond a certain point. The sun faces a similar problem, but on a vastly larger scale. Scientists can observe patterns, but exact timing remains elusive. This unpredictability would matter less if the sun were irrelevant. But it is not. It is central. It is unavoidable. Every satellite orbit, every space mission, every astronaut depends on solar conditions. Even Earth's atmosphere expands and contracts in response to solar energy. During periods of high activity, atmospheric drag increases, affecting spacecraft orbits. The sun quietly influences things we rarely associate with it. And still, most people think of it as a constant yellow disk in the sky. This disconnect between perception and reality is dangerous. Not because the sun is malicious, but because assumptions breed complacency. Scientists do not fear the sun, but they respect it. They know that understanding the sun is not optional. It is essential, not just for astronomy, but for civilization itself. And despite decades of study, there are gaps, large gaps. The sun's magnetic cycle sometimes behaves oddly. Periods of unusually low activity have occurred in the past, coinciding with cooler climates on Earth. The relationship is complex and not fully causal, but the correlation is real. At other times, solar activity spikes unexpectedly. Why does this happen? Why do cycles vary in strength and duration? Why do magnetic patterns sometimes weaken or intensify without clear cause? These are not fringe questions. They are central to solar physics, and they remain unanswered. The sun matters more than any other star because it is the only one that can affect us directly. Its distance makes it benign most of the time, and dangerous when rare conditions align. Understanding those conditions is one of the greatest challenges in modern science. A star we cannot touch, the sun, feels close. It dominates our sky. Its light reaches us in just over 8 minutes. In cosmic terms, it is practically next door. And yet, it remains unreachable in the most fundamental way. No human has ever touched the sun. No probe has ever entered its surface. No instrument has ever sampled its core. For all its familiarity, the sun is one of the most inaccessible objects we study. This is not because we lack ambition. Humanity has sent machines to the edges of the solar system. We have landed on planets, flown past comets, and touched asteroids drifting through space. We have peered into the atmospheres of distant worlds and detected stars in other galaxies. But the sun resists direct contact. Its surface temperature exceeds 5,500 degrees Celsius, hot enough to vaporize any known material. Its radiation can destroy electronics in moments. Its magnetic environment is chaotic and violent. And deeper inside, conditions become utterly unthinkable. At the sun's core, temperatures reach around 15 million degrees Celsius. Pressure is so intense that atoms are crushed together continuously, forcing nuclear fusion to occur. No probe could survive even a fraction of that journey. No material could shield against such energy. Even approaching the sun is dangerous. As spacecraft move closer, solar radiation increases dramatically. The heat shields must endure temperatures that would melt steel instantly. Instruments must be protected from particle storms that can overload sensors and corrupt data. Every kilometer closer multiplies risk. This is why, for most of history, the sun was studied only from afar. Astronomers observed its light through telescopes, analyzing its spectrum to infer composition. They tracked sunspots as they crossed the surface, noting patterns and cycles. They watched flares erupt and fade, but these observations revealed only the surface. The sun's interior remained a black box. Unlike planets, the sun does not have a surface you can land on. What we see is the photosphere, a thin layer where light escapes into space. Below it lies a vast volume of plasma, churning and flowing, completely opaque to visible light. Nothing from the core travels straight outward. Photons produced by fusion take thousands of years to reach the surface, bouncing endlessly off charged particles. By the time they emerge, any information about their origin has been erased. This means that when we look at sunlight, we are seeing the result of processes that began long before human civilization existed. The sun we see today reflects conditions from the distant past. That delay creates uncertainty. If something changed deep inside the sun tomorrow, we would not know immediately. Its effects would take time to propagate outward, filtered through layers we cannot observe directly. This limitation forces scientists to rely on indirect methods. One of the most powerful of these is helioseismology, the study of vibrations within the sun. The sun constantly oscillates, producing waves that ripple across its surface. These waves are driven by convection and internal flows. By measuring how these waves move and change, scientists can infer conditions deep inside the sun. much like seismologists use earthquakes to probe Earth's interior. Helioseismology has revealed rotation patterns, internal flows, and structural boundaries. It has confirmed some theoretical predictions and raised new questions. For example, it showed that the Sun's interior rotates at different speeds depending on depth and latitude. The transition between different rotational regimes, known as the tachocline, plays a crucial role in magnetic field generation. But why this boundary behaves the way it does remains unclear. The Sun's magnetic field is generated deep inside, but its effects dominate the surface and beyond. And this magnetic field is responsible for sunspots, flares, and solar storms. Yet its exact origin and evolution are not fully understood. Magnetic field lines twist and tangle due to differential rotation. They store enormous amounts of energy. When they reconnect, that energy is released explosively. But predicting when and where this will happen remains difficult. Another indirect probe comes from neutrinos, nearly massless particles produced during nuclear fusion in the Sun's core. Neutrinos pass through matter almost unaffected, escaping directly from the core and reaching Earth in minutes. Detecting them is extraordinarily difficult. They rarely interact with anything. Massive detectors buried deep underground are required to catch even a handful. Yet these neutrinos provide direct confirmation that fusion is occurring as expected, and they validate core models. But they do not provide detailed images or dynamic information. They tell us fusion is happening. They do not tell us everything about how it behaves. This creates a paradox. We know the Sun is powered by fusion. We know its mass, age, and general structure. We know it will not suddenly explode or collapse. And yet, we cannot see inside it. This inability to directly observe the Sun's interior leaves room for uncertainty. Models must fill gaps. Assumptions must be made. And while most assumptions are well-founded, they are still assumptions. The Sun's plasma flows add further complexity. Convection near the surface drives rising and sinking currents. These flows interact with magnetic fields in non-linear ways. Small variations can cascade into larger changes. This makes the Sun sensitive to initial conditions. Two nearly identical states can evolve differently over time. This sensitivity limits predictability. Even with perfect models, long-term forecasting becomes difficult. The Sun is not chaotic in the everyday sense, but it exhibits complex behavior characteristic of nonlinear systems. This complexity explains why solar forecasting resembles weather forecasting. Short-term predictions are reasonable. Long-term predictions degrade. The Sun also exhibits phenomena that remain poorly explained. Sudden changes in activity levels, unusual patterns of sunspot emergence, variations in cycle length. These are not signs of danger, but they are signs of incomplete understanding. The challenge is compounded by scale. The Sun is enormous. Processes operate over vast distances and timescales simultaneously. As modeling everything accurately requires immense computational power and detailed physics. Even the best simulations simplify reality. This does not mean scientists are ignorant. It means the Sun is hard. It is a reminder that proximity does not guarantee accessibility. The Sun may be close in space, but it remains distant in understanding. And because it is so important, that distance matters. The Sun's violent side. From Earth, the Sun appears calm, a steady disk of light rising and setting with comforting regularity. It is easy to forget that this calm is an illusion created by distance. Beneath that gentle glow is a star in constant turmoil, releasing energy on scales that defy comprehension. The Sun is not quiet. It is not stable in the way a solid object is stable. It is dynamic, restless, and capable of sudden violence. But at any given moment, the sun's surface is alive with motion. Vast rivers of plasma flow beneath the photosphere. Hot material rises, cools, and sinks again in enormous convection cells larger than continents. Magnetic fields twist through this motion like invisible threads, storing energy as they are stretched and contorted. Most of the time, this energy remains contained. Sometimes, it does not. Solar flares are sudden releases of magnetic energy from the sun's surface. In a matter of minutes, they can unleash as much energy as billions of nuclear explosions. Light across the electromagnetic spectrum floods outward. Radio waves, X-rays, gamma rays, racing toward Earth at the speed of light. These events are not rare. Small flares happen daily. Larger ones occur less often. The most powerful flares are uncommon, but they do happen. And when they do, their effects extend far beyond the sun. A solar flare alone can disrupt radio communications on Earth, particularly on the side of the planet facing the sun. High-frequency radio signals can fade without warning. Navigation systems may lose accuracy. Satellites exposed to intense radiation can experience temporary or permanent damage. But flares are only part of the sun's violent nature. Even more powerful are coronal mass ejections, enormous eruptions that hurl billions of tons of charged plasma into space. These clouds of solar material expand as they travel, carrying embedded magnetic fields with them. When directed toward Earth, they can arrive in 1 to 3 days. Unlike light, these eruptions do not simply pass through. They collide with Earth's magnetic field. When this happens, the energy is transferred on a planetary scale. Earth's magnetosphere compresses. Currents surge through the upper atmosphere. Electrical systems on the ground can be overwhelmed. Transformers can overheat. Power grids can collapse. This is not speculation. In 1859, a powerful solar storm known as the Carrington event struck Earth. Telegraph systems sparked and caught fire. Operators received electric shocks. Auroras were visible near the equator. If a similar event occurred today, the consequences would be far more severe. Modern society is orders of magnitude more vulnerable. Satellites form the backbone of communication, navigation, weather forecasting, and finance. Power grids span continents. Systems are interconnected and sensitive. A major solar storm could disable satellites, disrupt power for weeks or months, and cause economic damage on a global scale. And yet, predicting such events remains difficult. The sun does not announce its eruptions long in advance. Magnetic stress builds invisibly beneath the surface. When it reaches a tipping point, reconnection occurs suddenly. Energy is released without warning. Scientists monitor sunspots, dark regions where magnetic fields are particularly strong, as indicators of potential activity. But not all sunspots produce flares, and some flares occur without obvious precursors. The sun does not follow schedules. This unpredictability challenges our assumption of safety. We rely on the sun's average behavior, but rare extremes matter more. It is not the everyday output that threatens infrastructure. It is the unusual event. The sun's violent side also includes high-energy particles accelerated during flares and eruptions. These particles can reach Earth in minutes, penetrating spacecraft and posing risks to astronauts. Radiation exposure during such events can exceed safe limits quickly. This is why human spaceflight beyond low Earth orbit must account for solar weather. The sun is not just a background presence. It is an active hazard. Yet despite its power, the sun is not malevolent. Its violence is a byproduct of physics, of magnetism interacting with plasma under rotation. The sun does not choose when to erupt. It follows natural processes that sometimes produce extreme outcomes. Understanding those processes is the challenge. Magnetic reconnection, the mechanism behind flares and eruptions, is complex. Field lines break and reconnect, converting magnetic energy into kinetic and thermal energy. This process occurs in many astrophysical contexts, but the sun provides the closest example. Even here, details remain unclear. Why do some regions store enormous energy while others do not? Why does reconnection occur suddenly rather than gradually? Why do some eruptions release energy upward into space while others collapse back onto the sun? These questions matter because they determine impact. A powerful eruption directed away from Earth is harmless. A weaker one aimed directly at us can cause disruption. Direction matters as much as strength. The sun's rotation complicates matters further. Active regions move across the surface. A sunspot group facing Earth today may rotate out of view tomorrow. Timing becomes critical. The sun's violent behavior is also cyclical. During solar maximum, activity increases. Flares and eruptions become more frequent. During solar minimum, the sun appears calmer. But this cycle is not perfectly regular. Some cycles are stronger than expected, others weaker. Occasionally, activity drops to unusually low levels for extended periods. These variations hint at deeper processes we do not fully understand. The sun's magnetic field undergoes a global reversal roughly every 11 years. North becomes south. South becomes north. This reversal is part of the solar cycle, but its timing and strength vary. Why does the reversal occur when it does? What controls its smoothness or turbulence? The answers lie deep within the sun, beyond direct observation. Violence on the sun is not limited to dramatic events. Constant outflows of solar wind shape the heliosphere. Subtle fluctuations in this wind influence Earth's radiation environment. Over time, these effects accumulate. The sun is always interacting with Earth, whether we notice it or not. This interaction is usually beneficial. Solar wind helps shield the solar system from high-energy cosmic rays. But changes in solar activity can alter this balance. Periods of low solar activity allow more cosmic radiation to reach Earth. Periods of high activity increase radiation exposure from the sun itself. Both have consequences. The sun's violent side is therefore not a single phenomenon. It is a spectrum of behavior, from gentle fluctuations to extreme outbursts. Most of the time, we experience only the mild end of this spectrum. But history shows that extremes are possible. And because the sun feels familiar, we are tempted to dismiss that possibility. But this is the danger of proximity. The sun is close enough to feel safe, yet powerful enough to demand respect. It is neither benign nor hostile. It is simply a star doing what stars do, under conditions that happen to matter greatly to us. The sun's surface is not what it seems. When we imagine the surface of the sun, we often picture a smooth, glowing sphere, a uniform ball of light hanging quietly in space. This image is comforting. It suggests simplicity. It suggests order. But the sun's surface is nothing like that. Up close, the sun is chaotic. What we call the sun's surface is not solid ground. It is the photosphere, a thin, turbulent layer of plasma where light finally escapes into space. Below it, the sun is opaque. Above it, the atmosphere grows thinner and stranger. This boundary is where the sun reveals its most visible clues. And those clues tell a story of constant instability. The photosphere is in perpetual motion. Hot plasma rises from below, cools, and sinks again in a process called convection. These motions form granules, bright, cellular patterns covering the entire surface. Each granule is roughly the size of a country, forming and dissolving within minutes. Nothing about this surface is still. Beneath this churning plasma, magnetic fields are being twisted and stretched. When these fields pierce the photosphere, they suppress convection, preventing hot material from rising. The result is a sunspot, a darker, cooler region embedded within the glowing surface. Sunspots have been observed for centuries. They appear, grow, shrink, and vanish. At times, they cover large portions of the sun. At other times, they are almost completely absent. At first glance, sunspots seem like surface blemishes, but they are far more than that. Each sunspot marks a region of intense magnetic activity. The magnetic fields in these regions are thousands of times stronger than Earth's magnetic field. These fields extend far above the surface, anchoring enormous loops of plasma that arch into the sun's atmosphere. Sunspots are the footprints of magnetic structures that reach deep into the sun's interior. Their presence reveals where magnetic energy is concentrated and where violent events are most likely to occur. Yet, sunspots behave strangely. They follow patterns. They tend to appear in bands north and south of the sun's equator. Over time, these bands migrate toward the equator, creating a pattern known as the butterfly diagram. And this pattern repeats roughly every 11 years, but not perfectly. Some cycles produce many sunspots, others produce fewer. Some cycles peak early, others linger. Occasionally, sunspots nearly disappear altogether for extended periods. These deviations are not fully understood. Sunspots are not merely indicators of surface behavior. They are symptoms of processes occurring deep below. Their number, size, and distribution reflect how magnetic fields are generated and transported within the sun. The problem is that we cannot observe those processes directly. When sunspots emerge, they do so suddenly. Magnetic fields rise from below the photosphere, breaking through in dramatic fashion. Why some magnetic structures rise while others remain buried is unclear. Even more puzzling is why sunspots often appear in pairs or groups, connected by invisible magnetic loops. These regions are prone to flares and eruptions, suggesting stored energy waiting to be released. But predicting which sunspot will erupt and when remains extremely difficult. Bright regions called faculae also appear on the sun's surface, often near sunspots. These areas emit more light than the surrounding photosphere, partially compensating for the dimming caused by sunspots. This interplay between dark and bright regions means that total solar brightness does not vary dramatically, even during active periods. The sun hides its variability behind balance. From a distance, the sun appears steady. Up close, it is anything but. The sun's surface also exhibits flows that defy intuition. Plasma does not simply rise and fall. It moves sideways, forming large-scale circulation patterns. These flows transport magnetic fields across the surface, redistributing energy and shaping future activity. One such flow, known as meridional circulation, carries material from the equator toward the poles and back again. This flow plays a role in the solar cycle, but its speed and structure vary in ways that challenge models. Sometimes it slows, sometimes it accelerates, sometimes it shifts unexpectedly. These changes may seem subtle, but they influence how magnetic fields evolve over years. Small differences can alter the strength of future cycles. This sensitivity makes the sun difficult to predict long-term. Another layer of complexity lies in the sun's differential rotation. The equator rotates faster than the poles. This differential motion stretches magnetic field lines, on amplifying them through a process known as the solar dynamo. The solar dynamo is the engine behind magnetic activity. It converts kinetic energy from plasma flows into magnetic energy. But the details of this process remain incomplete. Scientists know the dynamo exists. They can simulate aspects of it. But simulations struggle to reproduce all observed features simultaneously. Something is missing. The sun's surface reflects this gap in understanding. Patterns emerge, repeat, and then shift. Activity waxes and wanes. Some features persist longer than expected. Others vanish abruptly. The sun behaves like a system that is almost understood, but not quite. This is unsettling precisely because the sun feels so familiar. We are comfortable with stars being mysterious when they are distant. But the sun is our neighbor, and its unpredictability feels personal. And yet, the sun does not behave unpredictably in a random way. It follows rules. It obeys physics. The challenge is that those rules interact in complex ways. Magnetic fields interact with plasma flows. Rotation alters both. Feedback loops amplify small differences. Over time, the system evolves in ways that are difficult to forecast precisely. The sun's surface is therefore a record of deeper processes, a shifting map of forces we cannot see directly. Every sunspot, every bright region, every flare leaves a mark. Together, they form a language the sun uses to communicate its internal state. Learning to read that language is one of solar physics' greatest challenges. Despite advanced instruments and constant monitoring, scientists still struggle to predict major solar events reliably. Forecasts improve hours or days ahead, but long-term certainty remains elusive. This limitation matters because it affects preparedness. If we could predict major solar storms months in advance, mitigation would be possible. Satellites could be protected. Power grids could be adjusted. Astronauts could take shelter. But the sun does not provide such long warnings. It reveals its intentions only shortly before acting. This behavior reinforces the central theme. The sun is not hiding something in the sense of secrecy. It is hiding something in complexity. Its surface is a mask, not intentionally deceptive, but inherently incomplete. It shows effects, not causes. It reveals motion, not motivation. To understand what the sun may be hiding, we must look beyond what we see. We must connect surface behavior to interior dynamics, a magnetic generation, and energy transport. This requires patience, humility, and acknowledgement of uncertainty. The temperature mystery. If the sun followed common sense, this mystery would not exist. On Earth, heat behaves predictably. The closer you are to a fire, the warmer it becomes. Step away, and the heat fades. This principle feels so fundamental that we rarely question it. Heat flows outward. Energy disperses, distance cools. The sun violates this expectation. At the sun's visible surface, the temperature is about 5,500 degrees Celsius. That is already extreme by human standards. But move outward, away from the surface, into the sun's outer atmosphere, the corona, and temperatures soar to more than 1,000,000 degrees. Farther from the heat source, yet dramatically hotter. This should not happen. For decades, this contradiction has troubled solar physicists. It is known as the coronal heating problem, and it represents one of the most significant unsolved mysteries in astrophysics. Not because it threatens Earth directly, but because it challenges our understanding of how energy moves through plasma. The sun's corona is vast and faint. It extends millions of kilometers into space, visible to the naked eye only during total solar eclipses as a ghostly halo surrounding the darkened disk. Despite its low density, it is extraordinarily hot. This heat does not come from nuclear fusion. Fusion occurs only in the sun's core. Energy must somehow be transported outward and deposited into the corona in a way that overwhelms cooling processes. The question is not whether energy exists. The sun produces plenty of it. The question is how that energy is transferred upward so efficiently, and why it concentrates in the corona rather than dissipating smoothly. Several explanations have been proposed. None have been confirmed fully. One leading idea involves magnetic waves. The sun's surface is constantly vibrating due to convection. These motions can generate waves that travel along magnetic field lines into the corona. If these waves dissipate their energy there, they could heat the plasma. This idea is elegant. It relies on known physics. But measuring these waves and confirming their energy transfer has proven difficult. Observations suggest they exist, but whether they carry enough energy remains debated. Another theory involves tiny magnetic reconnection events, often called nanoflares. These are miniature versions of solar flares, occurring constantly across the sun's surface. Individually, they release little energy. Collectively, they could heat the corona. The challenge is detection. Nanoflares are small, fast, and hard to distinguish from background activity. Proving their existence at the required scale has been elusive. The corona may be heated by a combination of processes rather than a single mechanism. Waves, reconnection, turbulence, all interacting in complex ways. This complexity makes definitive answers difficult. What is unsettling is that this mystery exists in our closest star. The sun is the most studied star in the universe. Its behavior is monitored continuously by space-based observatories. If we cannot explain why its atmosphere is hotter than its surface, it raises questions about our understanding of stars in general. And the coronal heating problem is not a niche curiosity. It touches on fundamental plasma physics relevant across the universe, from stellar winds to accretion disks to distant galaxies. The sun's corona also plays a crucial role in space weather. Solar wind originates there. Magnetic field structures extend outward from it. Understanding how the corona behaves is essential for predicting solar storms. Yet, even basic properties remain uncertain. The corona is structured by magnetic fields. Loops of plasma trace field lines, forming arches that can span hundreds of thousands of kilometers. These loops glow in X-rays and ultraviolet light, revealing temperatures far beyond what the surface could produce directly. Why these loops remain hot is part of the mystery. Plasma should cool rapidly by radiating energy away, and something must replenish that energy constantly. Otherwise, the corona would collapse into cooler states. Observations show that heating is not uniform. Some regions are hotter than others. Active regions around sunspots exhibit intense heating. Quiet regions remain hot but less active. Coronal holes, areas where magnetic fields open into space, are cooler but still far hotter than the surface. This variation suggests multiple heating mechanisms operating simultaneously. The sun's magnetic complexity again emerges as a likely culprit. Field lines twist, braid, and reconnect. Each interaction releases energy, but quantifying this process is difficult. The corona is also dynamic. Structures form and dissolve. Loops brighten and fade. Plasma flows along invisible pathways. These changes occur on timescales ranging from seconds to days. The sun's outer atmosphere behaves like a living system, constantly adapting, reacting, and evolving. Yet unlike living systems, it obeys physical laws. The challenge is that those laws interact across scales too wide for easy intuition. The coronal heating problem highlights a broader theme. Even when we know the rules, predicting outcomes in complex systems remains difficult. The sun does not hide its corona. It displays it openly during eclipses. It reveals it through radiation. And still, its behavior resists explanation. This is not because scientists lack data. It is because the data reveal complexity rather than simplicity. The corona may be heated by countless small events rather than a few large ones. This distributed heating is harder to detect and model, yet it requires instruments capable of resolving tiny changes over vast areas. Recent missions have begun to probe the corona more closely than ever before. They have detected magnetic waves, observed fine structures, and measured plasma flows. These observations have narrowed possibilities, but have not closed the case. Instead, they have revealed new layers of complexity. The sun's temperature mystery also connects to its magnetic cycle. During periods of high activity, coronal heating increases. During quieter periods, it decreases. But the relationship is not linear. Some cycles produce hotter coronae than expected. Others do not. This inconsistency suggests that internal dynamics modulate heating efficiency. Once again, the sun's interior asserts its influence. Energy generated deep within the core ultimately shapes behavior far above the surface. Small changes in interior flows can alter magnetic field generation, which in turn affects coronal heating. This chain of influence spans millions of kilometers and thousands of years. Understanding it requires connecting cause and effect across enormous gaps. The coronal heating problem remains unsolved not because it is impossible, but because it sits at the intersection of many difficult problems. Plasma turbulence, magnetic reconnection, wave dissipation, nonlinear dynamics. Each area is complex on its own. Combined, they create a puzzle that resists clean solutions. What makes this mystery compelling is not just its technical difficulty, but its familiarity. We see the sun every day. We feel its warmth. And yet, we do not fully understand how its atmosphere stays hot. This gap between experience and understanding is unsettling. It reminds us that proximity does not guarantee mastery, that even the nearest star can challenge fundamental assumptions. The sun is not hiding danger in this mystery, but it is hiding knowledge. Knowledge about how energy moves through plasma, about how magnetic fields store and release power, about how stars interact with their surroundings. Solving the coronal heating problem would not just explain the sun, it would illuminate processes occurring across the universe. And until it is solved, the sun remains an object of quiet uncertainty. Magnetic fields beyond control. If the sun were stripped of its magnetic field, it would be a far quieter star. Flares would fade. Storms would weaken. The surface would appear calmer, more predictable. Much of the sun's mystery would vanish. But the sun is not magnetically simple. Its magnetic field is vast, tangled, and constantly changing. It stretches from deep within the solar interior to far beyond the orbit of Earth. It twists through plasma like invisible tensioned wires, storing energy, releasing it suddenly, and reshaping space around the sun. This magnetic field is the true architect of solar behavior. Unlike Earth's relatively stable magnetic field, the sun's field is dynamic and chaotic. It is generated by motion, by the flow of electrically charged plasma moving inside the sun. Rotation, convection, and turbulence combine to create a stellar dynamo that produces magnetism on an enormous scale. But this dynamo does not operate smoothly. The sun does not rotate as a solid object. Its equator spins faster than its poles. Deeper layers rotate at different speeds than the surface. This differential rotation stretches magnetic field lines, winding them tighter over time. As these field lines twist, they store energy. The more they twist, the more energy they contain. Eventually, they reach a breaking point. When that happens, magnetic reconnection occurs. Reconnection is a violent process. Field lines snap and realign, releasing stored energy in an instant. This energy accelerates particles, heats plasma, and drives flares and eruptions. It is the spark behind the sun's most dramatic behavior. Yet, reconnection is difficult to predict. The buildup of magnetic stress happens invisibly. The release occurs suddenly. From the outside, the sun can appear calm right up until the moment it erupts. This unpredictability is one of the greatest challenges in solar physics. Scientists can map the sun's magnetic field at the surface. They can measure its strength and orientation. They can track how it evolves over days and weeks. But the most important interactions occur below the surface, out of sight. The sun's interior magnetic field cannot be observed directly. Its behavior must be inferred from surface patterns, flows, and timing. This indirect approach leaves room for uncertainty. The magnetic field also organizes the sun's atmosphere. Coronal loops trace magnetic field lines, glowing where plasma is trapped and heated. These loops can persist for hours or days, then suddenly collapse during eruptions. Why some loops remain stable while others destabilize is not fully understood. Magnetic fields also guide the solar wind, the constant stream of charged particles flowing outward from the sun. Where field lines are closed, plasma remains trapped. Where they open, particles escape into space. Changes in magnetic topology alter the solar wind's structure and intensity. These changes propagate outward, affecting the entire heliosphere. The sun's magnetic field also undergoes a complete reversal approximately every 11 years. North becomes south. South becomes north. This reversal marks the peak of solar activity. But the reversal is not smooth. Sometimes it occurs unevenly, with one hemisphere leading the other. Sometimes it stalls. Sometimes it happens more rapidly than expected. These irregularities suggest that the underlying dynamo is more complex than models capture. Historical records show periods when the sun's magnetic activity dropped dramatically. During these times, sunspots nearly vanished. The sun entered prolonged quiet phases. Why this happens remains unclear. Magnetic field generation depends on flows deep inside the sun. If those flows change, slow down, shift, or reorganize, magnetic activity changes with them. But we cannot see those flows directly. This leaves scientists watching surface behavior for clues. The sun's magnetic complexity means it cannot be fully controlled or forecasted. Predictions improve on short timescales, but long-term certainty remains out of reach. The sun's magnetic system behaves like a nonlinear engine, sensitive to initial conditions and prone to sudden transitions. This is not unique to the sun. Similar processes occur in other stars, in accretion disks, and in planetary magnetospheres. But the sun is the only example close enough to study in detail. And even here, magnetism resists mastery. The sun's magnetic field also stores memory. Past activity influences future behavior. Magnetic structures left behind from previous cycles affect how new fields emerge. This memory complicates prediction further. A solar cycle is not independent. It is part of a longer magnetic story. This long-term evolution may explain why some cycles are unexpectedly weak or strong. But without direct access to the interior, confirmation remains elusive. The sun's magnetism is not hiding malicious intent. It is hiding complexity. It operates under known laws, but those laws interact across scales that challenge comprehension. Magnetism is invisible, but its consequences are not. Every solar flare, every coronal mass ejection, every burst of radiation traces back to magnetic tension released. The sun's violence is magnetic violence. Understanding this magnetism is essential not only for science, but for safety. Space weather forecasting depends on it. Protecting technology depends on it. Planning human exploration beyond Earth depends on it. And yet, the magnetic heart of the sun remains partially concealed. The sun shows us the results, not the process. The solar cycle that broke expectations. For most of the 20th century, the sun appeared to follow a reassuring rhythm. Activity rose and fell in predictable waves. Sunspots increased, peaked, then faded away, only to return again roughly 11 years later. This pattern became known as the solar cycle, and for a time, it gave scientists confidence. The sun, it seemed, had a heartbeat. Each cycle followed a familiar arc. During solar minimum, the sun looked calm. Few sunspots appeared. Flares were rare. The magnetic field looked orderly. Then gradually, activity increased. Sunspots multiplied. Magnetic fields grew tangled. Flares and eruptions became more frequent. Eventually, the cycle peaked, solar maximum, before declining again. This pattern repeated often enough to feel dependable. But the sun has never promised regularity. As measurements improved and records lengthened, cracks appeared in this simple picture. Not every cycle looked the same. Some were stronger, some weaker. Some peaked early, others lingered. The sun followed the cycle, but not precisely. Then came cycles that behaved in ways no one expected. In the early 21st century, scientists noticed something unsettling. Our solar activity was declining more than models predicted. Sunspot numbers dropped. Magnetic fields weakened. The sun entered a prolonged, quiet phase that did not fit comfortably within established expectations. This was not unprecedented. Historical records show similar periods, including the Maunder minimum in the 17th century, when sunspots nearly vanished for decades. But seeing such behavior again in the modern era forced a re-evaluation. The sun had not changed the rules. We had misunderstood them. The solar cycle is driven by the sun's magnetic dynamo, the process by which plasma flows and rotation generate magnetic fields. This dynamo is influenced by deep interior flows, including differential rotation and convection. Small changes in these flows can alter the entire cycle. The problem is that these flows are hidden. We infer their behavior from surface patterns, but the connection is indirect. When a cycle weakens unexpectedly, it suggests something has shifted deep inside the sun. What shifted? Why? And how long will it last? These questions remain open. One possibility is that the sun's dynamo operates in multiple modes. Sometimes it produces strong cycles, sometimes weaker ones. Transitions between modes may occur irregularly, driven by internal turbulence. Another possibility is that long-term variations overlay the 11-year cycle, modulating its strength over decades or centuries. These longer cycles are harder to detect and harder still to predict. The sun may not have a single rhythm, but several interacting ones. This complicates forecasting dramatically. When scientists attempt to predict future cycles, they rely on indicators from the current one. Magnetic field strength near the poles, flow speeds, sunspot emergence patterns. These indicators provide clues, but they are not guarantees. Sometimes predictions fail. A predicted strong cycle turns out weak. A quiet sun becomes unexpectedly active. These failures are not due to carelessness. They reflect the sun's complexity. The solar cycle also exhibits asymmetry. The northern and southern hemispheres do not always behave the same way. One hemisphere may become active earlier or peak higher than the other. This imbalance suggests that magnetic field generation is not globally synchronized. Why does one hemisphere lead? Why does the imbalance sometimes reverse? Again, the answers lie deep inside the sun. The solar cycle also influences the sun's overall energy output, though the variation is small. Total solar irradiance changes by about 0.1% across a cycle. This is enough to influence Earth's upper atmosphere, but not enough to explain long-term climate changes on its own. Still, the connection between solar variability and Earth's environment remains an active area of research. Periods of prolonged low activity have coincided with cooler climates in the past. The relationship is complex, involving feedbacks and other factors. What matters most is not dramatic change, but uncertainty. The sun's cycles remind us that stability is dynamic. The sun maintains equilibrium not by remaining static, but by constantly adjusting. These adjustments sometimes produce behavior that defies expectation. The quiet sun is not necessarily safe. Low activity can mean weaker magnetic shielding against cosmic radiation. It can alter the heliosphere's structure. It can change the radiation environment of the solar system. High activity brings different risks: storms, flares, and disruptions. Either way, the sun's cycle shapes conditions in space and near Earth. The cycles that broke expectations forced scientists to confront uncomfortable truths. Models were incomplete. Assumptions needed revision. The sun was not as predictable as hoped. This realization marked a shift in solar physics. Instead of seeking perfect forecasts, scientists began focusing on probabilities, ranges, and uncertainty. The goal became preparedness rather than prediction. Understanding the sun meant accepting limits. This acceptance does not weaken science. It strengthens it. It acknowledges complexity rather than denying it. The sun's unexpected cycles also highlight how little we know about stellar dynamos in general. If we struggle to understand our closest star, understanding distant stars becomes even more challenging. The sun becomes both example and warning. It shows what stars can do. It shows what we cannot yet explain. The sun's hidden interior. Everything the sun does on its surface begins deep within. Every flare, every cycle, every magnetic twist traces back to regions no human eye has ever seen. The sun's interior is the engine room of its behavior, and it remains largely hidden. We know the sun has layers. That much is clear. But knowing that layers exist is not the same as understanding how they behave. At the very center lies the core, a region where pressure is so immense that hydrogen atoms are forced together continuously. This is where nuclear fusion occurs, releasing energy that ultimately becomes sunlight. The core is stable, dense, and unimaginably hot. But stability does not mean simplicity. Energy produced in the core does not flow outward freely. It is trapped, scattered, absorbed, and re-emitted countless times as it moves through the surrounding layers. Photons created by fusion can take tens of thousands of years to reach the surface. By the time they escape, they carry no direct memory of where they began. This long delay disconnects cause and effect. If conditions in the core change, the surface does not respond immediately. The sun can hide internal changes for centuries. This makes real-time diagnosis impossible. Surrounding the core is the radiative zone, where energy moves outward primarily through radiation rather than motion. In this region, plasma is relatively calm compared to the layers above. Yet even here, subtle motions and magnetic fields may exist, influencing energy transport in ways not fully understood. Above the radiative zone lies the convection zone. a turbulent region where hot plasma rises, cools, and sinks in vast circulating currents. This is where much of the sun's visible activity originates. These convective motions interact strongly with rotation, creating the conditions necessary for magnetic field generation. The boundary between the radiative zone and the convection zone is known as the tachocline. This thin, transitional layer plays a critical role in the solar dynamo, or it is here that differential rotation is most pronounced. It is here that magnetic fields are stretched, amplified, and organized. And it is here that uncertainty deepens. The tachocline is not directly observable. Its properties must be inferred through helioseismology, by studying how sound waves travel through the sun. These measurements have revealed its existence, but not its full behavior. Why is this layer so effective at generating magnetic fields? Why is it stable over long periods yet capable of change? How does turbulence above interact with calm below? These questions remain open. Helioseismology has shown that the sun's interior rotates differently at different depths. The core may rotate more uniformly than the surface. The convection zone exhibits differential rotation. These variations create shear, differences in speed that stretch magnetic field lines. Shear is essential for the dynamo. Without it, the sun's magnetic field would weaken and fade. But too much shear could destabilize the system. The sun exists in a narrow range where magnetism is sustained without destroying coherence. How the sun maintains this balance is unclear. Even more puzzling is evidence that the sun's internal flows change over time. Helioseismic measurements suggest that flow patterns vary across cycles. Meridional circulation speeds up and slows down. Convection patterns shift. These changes correlate with variations in solar activity. Correlation does not prove causation, but the connection is suggestive. If internal flows modulate the solar cycle, then understanding them is essential for prediction. Yet these flows are hidden, indirect, and difficult to model accurately. The sun's interior may also host magnetic fields stronger and more organized than those seen at the surface. These fields could store energy over long timescales, releasing it gradually or suddenly depending on conditions. Such hidden reservoirs would explain why solar activity sometimes deviates from expectations. They would act as memory, carrying influence from one cycle to the next. But confirming their existence is difficult. Neutrinos provide one of the few direct probes of the core. Detected on Earth, they confirm that fusion occurs at expected rates. But neutrinos reveal little about flow patterns, magnetic fields, or subtle structural changes. They tell us the engine is running. They do not reveal how smoothly it runs. The sun's interior may also contain waves, gravity waves, not to be confused with gravitational waves, generated by convective motions. These waves could transport energy and angular momentum, influencing rotation and magnetic behavior. Detecting such waves is challenging. Their signals are faint, their effects subtle, but they may play a role in regulating the sun's internal dynamics. If so, they add another layer of complexity. The hidden interior also raises questions about long-term evolution. The sun has existed for about 4.6 billion years. Over that time, its internal structure has changed slowly. Fusion rates have increased. Composition has evolved. Rotation has slowed. These gradual changes influence magnetic behavior. The sun today is not the sun of the past, yet our models often treat it as static over short timescales. This approximation works reasonably well, but it may obscure slow trends that influence cycle behavior. The interior may also respond to external influences. Tidal interactions with planets are weak, but not zero. Whether they have measurable effects remains controversial. Most evidence suggests they are negligible, but the debate itself highlights uncertainty. The sun's interior remains a place where theory outpaces observation. Models grow more sophisticated, incorporating turbulence, rotation, and magnetism. Simulations reproduce some features well, others resist explanation. This gap between model and reality is not failure. It is invitation. It invites deeper study, better instruments, and humility. The sun's hidden interior is not hiding danger. It is hiding complexity. It is hiding feedback loops, delays, UN interactions that challenge linear thinking. Everything we see on the surface, sunspots, flares, cycles, is the visible expression of processes occurring far below. Understanding the sun means understanding those processes. And until we do, the sun will continue to surprise us. Not because it is unpredictable, but because our understanding is incomplete. Listening to the sun. The sun does not speak in words, but it is never silent. Beneath its blazing surface, the entire star vibrates. It expands and contracts rhythmically, sending waves rippling through its interior. These vibrations are subtle, invisible to the naked eye. Yet they carry some of the most valuable information scientists have ever obtained about the sun's hidden depths. This is how we listen to the sun. The technique is called helioseismology, and it works on a simple principle. Just as earthquakes send seismic waves through Earth, disturbances inside the sun generate sound waves that travel through its plasma. These waves bounce, refract, and interfere, eventually reaching the surface where they cause tiny motions, rises and falls measured in mere meters. By observing these surface oscillations with extreme precision, scientists can infer what lies beneath. Every wave carries information about the material it passed through. Changes in temperature, density, and motion alter how waves travel. By analyzing millions of such oscillations, researchers build three-dimensional maps of the sun's interior. This achievement is extraordinary. Without touching the sun, without entering it, humanity has learned to probe its inner structure using sound alone. Helioseismology has confirmed the existence of layers, revealed rotation patterns, and exposed hidden flows. And yet, even this powerful tool has limits. The sun's vibrations are complex. Thousands of modes overlap, creating a symphony of motion that must be disentangled mathematically. Extracting meaningful signals requires long-term observation, careful modeling, and constant refinement. What helioseismology has revealed is both reassuring and unsettling. It confirms that the sun's basic structure matches theoretical expectations. The core, radiative zone, convection zone, and tachocline all exist as predicted. Rotation varies with depth and latitude. These findings validate decades of stellar theory, but helioseismology has also revealed surprises. One of the most striking discoveries is that the sun's interior does not rotate uniformly. The convection zone shows strong differential rotation, while the radiative zone rotates more rigidly. The transition between these regimes is sharp and persistent. Why this boundary behaves the way it does remains unclear. Helioseismic data also show that internal flows change over time. Meridional circulation, the slow flow of plasma from equator to poles and back, varies in speed and structure. These changes correlate with solar activity cycles. This suggests that the sun's interior is not static, even on decadal timescales. Some oscillation modes hint at structures or behaviors not fully explained by current models. Subtle anomalies appear in wave travel times. Small asymmetries emerge between hemispheres. These features are not dramatic enough to rewrite theory, but they are persistent enough to resist dismissal. They suggest that something in the sun's interior is more complex than our models capture. Listening to the sun also reveals how energy and momentum move inside it. Waves can transport angular momentum, redistributing rotation rates. They can interact with magnetic fields, influencing the solar dynamo indirectly. These interactions are difficult to quantify, but they matter. The sun's oscillations also change with the solar cycle. During periods of high activity, wave properties shift slightly. Frequencies change. Damping rates increase. These variations reflect changes in magnetic conditions near the surface and possibly deeper inside. This means the sun's vibrations carry information not just about structure, but about state. In a sense, the sun's sound changes as it becomes more active or more quiet. Helioseismology has also provided hints about the sun's core rotation. Some studies suggest the core may rotate faster than the layers above it. Others suggest more uniform rotation. The data are difficult to interpret, and conclusions remain tentative. If the core does rotate differently, it could influence long-term magnetic behavior. A slowly evolving core could store angular momentum and energy, releasing influence gradually over time. Such a mechanism would help explain long-term variations in solar activity. But confirming this requires better data. Listening to the sun is complicated by noise. Surface turbulence generates background motion that obscures deeper signals. Separating these effects requires long observations and statistical techniques. Even then, ambiguity remains. The sun does not reveal its secrets easily. Helioseismology also highlights a philosophical point. Our understanding of the sun depends on interpretation. We measure vibrations at the surface, then infer interior conditions using models. If the models are incomplete, interpretations may be biased. This does not invalidate the technique. It simply reminds us that indirect observation always carries uncertainty. The sun's sounds are clues, not confessions. Still, these clues are invaluable. Without helioseismology, the sun's interior would remain almost entirely unknown. With it, we have glimpses, enough to confirm broad structure, enough to identify mysteries, but not enough to resolve everything. The sun is speaking. We are listening. But we do not yet understand every word. As instruments improve, helioseismic measurements become more precise. Longer data sets reveal subtle trends. New analysis techniques extract information previously buried in noise. Each improvement sharpens our picture and often reveals new questions. This pattern repeats throughout solar science. Every answer uncovers deeper complexity. Listening to the sun also reinforces a theme that has emerged repeatedly. The sun is not hiding a single secret. It is hiding many, layered within each other, connected through processes that span scale and time. It is not a puzzle with one missing piece. It is a system whose full behavior emerges only when many pieces are understood together. Helioseismology brings us closer to that understanding. But not all the way. The sun is changing. The sun feels eternal. It rises each day with the same warmth, the same light, like the same reassuring presence. Human lifetimes are too short to notice its slow transformations. But over longer timescales, the sun does change, subtly, gradually, and sometimes in ways that matter profoundly. Change does not always announce itself dramatically. In the sun, change often appears as small shifts. A slightly altered rhythm, a quieter cycle, a modest variation in brightness. These shifts are easy to overlook. Yet when studied carefully, they suggest that the sun is not a perfectly constant star. Measurements of solar output show that the sun's brightness varies over time. The variation is small, only about 0.1% across a solar cycle, but it is real. These changes influence Earth's upper atmosphere, affecting temperature, density, and circulation patterns. Over long periods, even small variations can have cumulative effects. The Sun's activity level also changes beyond the familiar 11-year cycle. Historical records reveal extended periods of unusually low or high activity. These periods lasted decades, sometimes longer, and coincided with notable changes in Earth's environment. One of the most famous examples is the Maunder minimum, a period during the 17th century when sunspots nearly disappeared for about 70 years. During this time, Europe experienced colder winters and shorter growing seasons. While the sun was not the sole cause of these conditions, its reduced activity likely played a contributing role. What caused the sun to enter such a prolonged quiet phase remains uncertain. Solar dynamo models can reproduce shorter cycles reasonably well, but extended minima challenge understanding. And something in the sun's interior must have changed, something that altered magnetic field generation for decades. The sun eventually recovered. Sunspots returned. Cycles resumed. But the episode left a lingering question. Could it happen again? Modern observations show that solar cycles vary significantly in strength. Some recent cycles have been weaker than those of the mid-20th century. This decline has sparked debate. Is it a temporary fluctuation or the beginning of a longer trend? Scientists do not agree. Some argue that the sun is entering another extended minimum. Others suggest that variability will rebound in future cycles. The data are insufficient to draw firm conclusions. This uncertainty matters because long-term changes in solar activity affect Earth's space environment. Reduced solar wind weakens the heliosphere, allowing more cosmic radiation to reach the inner solar system. Increased cosmic radiation can influence satellite electronics, aviation exposure, and possibly cloud formation. Conversely, increased solar activity brings more frequent storms and radiation hazards. The sun's changing behavior therefore presents different challenges depending on direction. Another sign of change lies in the sun's rotation. Over billions of years, the sun has slowed down. Magnetic braking, the loss of angular momentum through the solar wind, gradually reduces rotation speed. This slowdown affects the solar dynamo, altering magnetic field generation. A slower rotating sun produces different magnetic patterns than a faster one. This evolutionary change influences activity levels and cycle characteristics. The sun we observe today is not the sun that existed billions of years ago. Even over shorter timescales, rotation patterns shift subtly. Helioseismic studies show that internal flows evolve. These changes may precede or follow variations in surface activity, suggesting feedback between interior and exterior. The sun's magnetic field also shows long-term trends. Polar field strengths vary from cycle to cycle. These fields influence the strength of the next cycle. Weak polar fields often precede weak cycles. This relationship offers some predictive power, but not certainty. The sun's evolution is not linear. It does not progress smoothly from one state to another. It oscillates, adjusts, and occasionally surprises. Understanding whether current trends represent noise or signal is one of the most pressing challenges in solar physics. The difficulty lies in limited data. Modern observations span only a few decades with high precision. Earlier records rely on proxies, sunspot counts, auroral reports, isotope concentrations in ice cores, and tree rings. These proxies provide valuable insights, but they are indirect and incomplete. They suggest that the sun has experienced variability throughout its history. Periods of calm, periods of activity, transitions between states. What they do not provide is a clear mechanism. Why does the sun sometimes enter extended quiet phases? Why does activity sometimes intensify unexpectedly? Are these changes random, or do they follow hidden patterns? The sun's slow changes challenge the assumption of constancy that underlies many models. Climate models, space weather forecasts, and long-term planning often assume that the sun's average behavior remains stable. If that assumption is wrong, consequences follow. This does not mean catastrophe is imminent. The sun will not suddenly change dramatically, but gradual trends matter over decades and centuries. Recognizing that the sun changes does not mean fearing it. It means respecting complexity. The sun is not a static machine. It is a dynamic system evolving under the influence of internal physics and long-term processes. This evolution is slow compared to human lifetimes, but fast compared to geological timescales. The sun's changing behavior also reminds us that understanding requires patience. Patterns emerge only with long observation. Short data sets can mislead. Science advances by accumulation. As we continue this exploration, we will examine how the sun's changing behavior intersects with Earth's vulnerability. Modern society depends on stable conditions in space. Even modest changes in solar behavior can test that dependence. Understanding what the sun is doing and what it may do is not an abstract pursuit. It is practical. The sun may not be hiding something dramatic. It may be hiding gradual change, subtle, persistent, and easy to ignore until its effects accumulate. Solar storms and Earth's fragility. For most of human history, the sun's disturbances passed unnoticed. A flare erupted. A cloud of charged particles swept through space. Earth's magnetic field absorbed the impact, and life on the surface continued uninterrupted. The planet was resilient, and civilization was simple. That balance no longer exists. Modern Earth is fragile in ways our ancestors never had to consider. We have wrapped the planet in technology, satellites orbiting above, power grids stretching across continents, communication systems dependent on invisible signals. All of it operates within an environment shaped directly by the sun. When the sun is calm, this system works effortlessly. When the sun is disturbed, weaknesses emerge. Solar storms begin quietly. Magnetic stress builds on the sun's surface. Field lines twist tighter and tighter. Eventually, they snap. Energy is released. Plasma is hurled into space. If Earth lies in the path of that eruption, consequences follow. The first impact often comes in the form of radiation. High-energy particles accelerated near the sun can reach Earth in minutes. These particles penetrate spacecraft, interfere with electronics, and pose risks to astronauts. Even aircraft flying at high altitudes near the poles can experience increased radiation exposure. Then comes the slower, heavier wave, the coronal mass ejection. A cloud of charged plasma carrying its own magnetic field slams into Earth's magnetosphere. The planet's magnetic shield compresses, deflecting much of the energy, but not all. Currents surge through Earth's upper atmosphere. These currents induce secondary currents in long conductors on the ground. Power lines, pipelines, and communication cables become unintended pathways for electrical flow. Transformers overheat. Protective systems trip. Power grids can fail. This chain reaction is not theoretical. In March 1989, a solar storm caused a major power outage in Quebec. In less than 2 minutes, millions of people lost electricity. The grid collapsed under geomagnetically induced currents. That storm was moderate by historical standards. A stronger event could cause far greater damage. Modern power grids are interconnected and optimized for efficiency, not resilience. High-voltage transformers are expensive, specialized, and difficult to replace quickly. Damage to a few critical components could lead to prolonged outages lasting weeks or months. Satellites face similar vulnerability. Solar storms can degrade solar panels, damage electronics, and alter orbits by expanding Earth's atmosphere. Some satellites may fail permanently. Navigation systems rely on precise timing signals from space. Solar activity can disrupt these signals, reducing accuracy or rendering systems temporarily unusable. Financial transactions, transportation, and emergency services depend on this precision. Even the internet is not immune. Undersea cables and terrestrial networks can experience interference during severe geomagnetic storms. The sun does not need to target Earth deliberately. Geometry alone determines impact. A powerful eruption directed slightly off course may miss us entirely. A weaker one aimed directly at Earth can cause disruption. This randomness complicates risk assessment. The most dangerous storms are rare. But rarity does not equal insignificance. In complex systems, rare events often cause the greatest damage. The historical record offers warnings. The Carrington event of 1859 remains the most powerful solar storm on record. Telegraph systems failed worldwide. Operators reported sparks jumping from equipment. Auroras lit up skies far from the poles. If an event of similar magnitude occurred today, the effects would be global. Scientists estimate that the economic cost could reach trillions of dollars. Recovery could take years. The impact would not be limited to one nation or one industry. And yet, forecasting such events remains limited. Space weather monitoring has improved significantly. Satellites continuously observe the sun. Early warning systems can detect eruptions and estimate arrival times. But predicting severity remains difficult. Magnetic orientation matters. If the magnetic field carried by a coronal mass ejection aligns in a way that couples strongly with Earth's field, impact is severe. If alignment is unfavorable, damage is reduced. Determining this orientation in advance is challenging. Warnings may come hours before impact, enough to take some protective measures, but not enough to prevent all damage. This uncertainty defines Earth's fragility. The sun does not hide storms maliciously. It simply operates under physics that does not prioritize human convenience. Our vulnerability arises from dependence. The irony is that the sun enabled civilization by providing energy and stability. That same star now poses a risk to the systems civilization relies on. Understanding this risk does not require fear. It requires realism. Solar storms are natural. They have occurred throughout Earth's history. Life survived because biological systems are resilient. Technology, however, is less forgiving. This difference matters. The sun's influence on Earth extends beyond dramatic storms. Continuous solar activity shapes the radiation environment. It affects atmospheric chemistry. It alters satellite lifetimes. These effects accumulate over time. Most of the time, they are manageable. But extreme events test margins. Earth's fragility is therefore not a weakness of the planet, but of modern systems. The sun exposes that fragility when it behaves unusually. Preparing for this reality requires understanding the sun better. Not just its average behavior, but its extremes. This brings the narrative back to the central question. If the sun is hiding something, it may not be a sudden catastrophe. It may be a lack of understanding about how often extreme events occur, how strong they can be, and how they unfold. Uncertainty itself is the risk. Could the sun surprise us? The most unsettling questions about the sun are not about what it does regularly, but about what it might do rarely. Science excels at describing average behavior. It models typical cycles, expected ranges, and most likely outcomes. But nature does not always operate within averages. Sometimes, it produces events that sit far outside normal expectations, events that occur infrequently, but with disproportionate impact. The sun is no exception. Most solar activity is mild. Small flares, gentle variations in brightness, modest storms that ripple harmlessly through space. These events dominate observations and shape our sense of normalcy. But the sun is capable of more. Evidence from Earth itself suggests that extreme solar events have occurred in the past. Tree rings preserve traces of increased radiation exposure. Ice cores capture chemical signatures linked to energetic particles. These records hint at solar storms far stronger than any observed in the modern technological era. And these events did not announce themselves dramatically at the time. Human civilization was not equipped to notice them. But their traces remain, locked into natural archives. The implication is clear. The sun can surprise us. One such event appears to have occurred around the year 775. Tree ring data show a sudden spike in carbon-14, likely caused by an intense influx of high-energy particles from space. The most plausible source is an extreme solar storm, one far more energetic than anything recorded since. If such an event happened today, the effects would be unprecedented. And yet, we do not know how often such events occur. Are they once-in-a-millennium anomalies? Are they more frequent than we assume? Are we simply lucky to have avoided them in recent history? The uncertainty itself is troubling. Models of solar behavior are based largely on observations from the past few centuries, a narrow window in the sun's long life. Extreme events may be underrepresented simply because we have not observed long enough. The sun's magnetic system stores energy over time. In principle, it could release that energy in bursts larger than any seen recently. Whether it will do so again is unknown. The sun's ability to surprise is not limited to storms. Sudden changes in activity patterns could occur. Prolonged quiet phases could return. Magnetic configurations not seen in recent cycles could emerge. These possibilities do not violate known physics. They exist within the boundaries of what the sun can do. The question is not whether they are possible. It is whether we are prepared. Scientists approach this uncertainty cautiously. Thus, they do not predict catastrophe without evidence. But they also do not dismiss low-probability risks when consequences are high. Instead, they study proxies. They extend datasets backward using natural records. They compare the sun to similar stars. They simulate extreme scenarios to test system resilience. This approach acknowledges limits. We cannot control the sun. We cannot eliminate uncertainty. We can only reduce ignorance. One reason extreme solar events are difficult to predict is that they may arise from rare combinations of factors. Magnetic fields align in unusual ways. Energy accumulates over longer than normal periods. Reconnection occurs across larger regions. These conditions may not appear in short data sets. The sun's complexity means that rare events may not scale smoothly from common ones. Sir, the biggest storms may not simply be larger versions of smaller storms. They may involve different dynamics altogether. This possibility complicates extrapolation. Another source of surprise lies in interaction effects. The sun does not exist in isolation. It interacts with the heliosphere, the interstellar medium, and planetary magnetic fields. Changes in one component can influence others. For example, A weaker heliosphere allows more cosmic radiation into the solar system. Increased radiation can affect satellite electronics and aviation even without a solar storm. The sun's influence therefore extends beyond its own eruptions. The idea that the sun could surprise us does not imply imminent danger. It implies humility. It reminds us that even familiar systems can behave unexpectedly under certain conditions. This is a recurring theme in science. Earthquakes, volcanic eruptions, extreme weather, all occur within systems that are well studied, yet still capable of producing surprises. The sun belongs to this category. Recognizing this does not diminish scientific understanding. It refines it. The sun's potential for surprise also reframes our relationship with it. The sun is not a static background object. It is an active participant in Earth's environment. Its behavior influences conditions in space continuously. Modern civilization has extended into that space. Satellites orbit within the sun's reach. Astronauts venture beyond Earth's magnetic protection. Plans for lunar bases and Mars missions depend on understanding solar radiation risks. Surprises become more consequential as exposure increases, and this is why space agencies invest heavily in solar monitoring. Continuous observation reduces uncertainty. Early warnings provide time to respond. Improved models narrow risk ranges, but they cannot eliminate unknowns entirely. The sun will always retain some capacity to surprise. This realization leads to a subtle shift in perspective. The question becomes less about predicting every event and more about designing systems resilient enough to withstand surprises. Resilience acknowledges uncertainty. It accepts that not everything can be foreseen. The sun's surprises are not acts of hostility. They are expressions of natural variability. They become threats only when systems lack tolerance. As we approach the final sections of this documentary, attention will turn to what scientists still do not understand. The open questions that remain unresolved despite centuries of study. These gaps do not signal failure. They signal opportunity. The sun is not hiding something dangerous out of malice. It is hiding complexity behind familiarity. And recognizing that complexity may be the most important step toward living safely beside a star we depend on, but do not fully control. What scientists still don't understand. For all that is known about the sun, the list of unanswered questions remains long. This may seem surprising. After all, the sun is the most studied star in the universe. It has been observed continuously for decades with sophisticated instruments. Entire scientific disciplines exist to understand its behavior. And yet, uncertainty persists. This uncertainty does not arise from ignorance. It arises from complexity. One of the most fundamental gaps in understanding lies in the solar dynamo, the mechanism that generates the sun's magnetic field. Scientists know that rotation and convection play central roles. They know that differential rotation stretches magnetic field lines. They know that turbulence amplifies and redistributes magnetic energy. But knowing the ingredients is not the same as knowing the recipe. Models of the solar dynamo can reproduce some observed features, but not all at once. A model that explains cycle length may fail to explain field strength. A model that produces realistic sunspot patterns may struggle with hemispheric asymmetry. No single model captures the full behavior of the sun's magnetism. This limitation matters because magnetic fields drive nearly all solar activity. Without understanding how they are generated and evolve, prediction remains uncertain. Another major unknown involves the sun's interior flows. Helioseismology has revealed large-scale circulation patterns, but their detailed structure remains unclear. Meridional circulation appears to vary with depth and time. Convection exhibits turbulence across a wide range of scales. These flows transport angular momentum and magnetic fields. Small changes can have large effects over years, but measuring these flows precisely is difficult. Signals are subtle. Noise is significant. Interpretations depend on models that may be incomplete. The Sun's core presents additional mysteries. While fusion rates appear stable, subtle variations cannot be ruled out entirely. Neutrino measurements confirm energy production, but they do not reveal flow patterns or magnetic structures. The core may rotate differently than surrounding layers. If so, it could store angular momentum and influence long-term magnetic behavior. Evidence for differential core rotation remains tentative. The Sun's atmosphere also resists full understanding. The coronal heating problem remains unresolved. Competing theories coexist. Observations support aspects of each, but none explain all features. Why is heating uneven? Why do some coronal structures persist while others collapse? Why does heating efficiency vary across cycles? These questions point to gaps in plasma physics under solar conditions. Another area of uncertainty involves the Sun's long-term variability. Historical proxies suggest extended periods of unusual behavior, but mechanisms remain unclear. Do these periods arise from random fluctuations or from organized changes in the dynamo? Are they predictable or inherently unpredictable? The Sun's interaction with Earth introduces further complexity. Solar variability influences Earth's atmosphere in subtle ways. Separating solar effects from other influences is challenging. Correlations exist, but causation is difficult to establish conclusively. This uncertainty feeds debate. The Sun's magnetic field also interacts with the heliosphere, shaping the boundary between solar and interstellar space. Changes in solar output alter this boundary, affecting cosmic radiation levels. The implications for Earth's radiation environment are still being explored. Even basic questions about the Sun's past remain open. Was the young Sun more active than today? How did its behavior influence early Earth? How did its magnetic field evolve over billions of years? These questions matter for understanding habitability, not just here, but around other stars. The Sun serves as a reference for stellar physics. If our understanding of it is incomplete, understanding other stars becomes even more uncertain. This realization is humbling. The Sun challenges the assumption that proximity guarantees comprehension. It reminds us that complexity does not disappear when something is close. What scientists still do not understand about the Sun is not hidden by secrecy. It is hidden by scale, by indirect observation, and by interactions that defy simple explanation. Every answer generates new questions. This is not a flaw of science. It is its nature. The Sun's remaining mysteries are active areas of research. New instruments provide higher resolution. Longer data sets reveal trends. Improved models incorporate more physics. Progress continues, but certainty remains elusive, getting closer than ever before. For centuries, the Sun was observed from a safe distance. Telescopes stayed on Earth. Instruments studied sunlight after it had already traveled through space. The Sun revealed itself only indirectly, filtered through atmosphere and distance. That era is ending. In recent decades, humanity has begun sending machines closer to the Sun than ever before. These missions are not acts of curiosity alone. They are responses to uncertainty. If the Sun is hiding something, the only way to uncover it is to approach the source. Getting close to the Sun is one of the most difficult challenges in space exploration. Heat increases rapidly with proximity. Radiation intensifies. Magnetic fields become unstable. The environment grows hostile in ways that push engineering to its limits. Every step inward requires new solutions. Spacecraft approaching the sun must shield themselves from temperatures that can melt steel. They must survive particle storms that can disrupt electronics. They must operate in a region where magnetic forces are strong enough to interfere with instruments. Despite these challenges, scientists have pressed forward. Modern solar missions are designed not just to observe the sun, but to experience it. They sample the solar wind at close range. They measure magnetic fields directly. They capture images of the sun's surface and atmosphere with unprecedented resolution. These missions represent a shift in strategy. Instead of inferring behavior solely from afar, scientists now gather data from within the sun's sphere of influence. This proximity provides insights impossible to obtain otherwise. Close-up observations have revealed fine structures in the solar atmosphere. Tiny magnetic loops, rapid plasma jets, and subtle waves propagating through the corona. These features were invisible in earlier data. The sun appears more textured, more dynamic, and more complex than previously imagined. Some observations support existing theories. Others challenge them. For example, measurements of the solar wind close to the sun show that it is not smooth or uniform. It is structured, variable, and sometimes turbulent. Magnetic field measurements reveal rapid changes and unexpected orientations. These findings complicate simple models. The closer scientists look, the more they realize that the sun's behavior cannot be reduced to a few dominant processes. Instead, it emerges from countless interactions occurring simultaneously. Proximity also reveals how energy flows from the surface into the atmosphere. Waves, jets, and reconnection events appear more frequently than expected. Some structures dissipate energy rapidly, others persist. This diversity suggests that coronal heating likely involves multiple mechanisms operating together. Close-range measurements also show that the sun's magnetic field is more tangled than surface maps suggest. Field lines twist and braid at small scales, storing energy that can be released in sudden bursts. This supports the idea that countless small reconnection events contribute to heating and variability. Yet, even with these insights, clarity remains elusive. Each new observation answers one question and raises several more. Structures are discovered, but their roles are debated. Patterns are seen, but their significance is uncertain. This is the cost of proximity. The closer you get, the more detail you see, and detail reveals complexity. Solar missions also provide critical data for space weather forecasting. Measuring conditions near the sun improves estimates of how storms evolve as they travel outward. This enhances early warning capabilities, giving Earth more time to prepare. But early warnings are not predictions. They are responses. The sun still decides when and how to act. Close-up observations have also challenged assumptions about solar stability. The sun's surface and atmosphere appear more variable on short timescales than expected. Changes occur rapidly, sometimes without obvious precursors. This variability suggests that the sun's behavior may be more sensitive to small-scale processes than previously thought. If true, this complicates forecasting further. Understanding the sun may require embracing uncertainty rather than eliminating it. The effort to get closer to the sun reflects a broader shift in science. Instead of seeking definitive answers quickly, scientists increasingly focus on characterizing variability, mapping distributions, and understanding probabilities. This approach acknowledges that complex systems may not yield simple rules. The Sun is one such system. Close-up exploration does not demystify the Sun completely. It reveals layers of behavior that were previously hidden. But it also shows that there is no single lever controlling solar activity. The Sun is not hiding one secret. It is hiding many. These missions represent humanity's willingness to confront uncertainty directly. They bring us closer to the Sun physically, even as they reveal the distance that remains in understanding. The star that controls our fate. Every civilization that has ever existed has lived under the same star. Long before science named it, measured it, or modeled it, the Sun shaped human survival. It determined where crops could grow, when seasons would change, and how long a day would last. Its influence was absolute, even when it was misunderstood. That influence has not diminished, it has deepened. Today, the Sun controls far more than daylight and warmth. It governs the environment in which modern civilization operates. An environment that extends far beyond Earth's surface. Satellites orbit within its reach. Spacecraft travel through its wind. Astronauts rely on its predictability for survival. The Sun has become an active participant in human affairs. Earth's atmosphere exists because of the Sun. Solar energy drives circulation, shapes climate, and sustains the delicate balance that keeps surface temperatures within livable bounds. Even Earth's magnetic field, our shield against radiation, evolved in response to solar conditions over billions of years. This balance feels permanent. It is not. The Sun's energy output has increased slowly over time. Billions of years ago, it was dimmer. Life adapted. Over billions more, it will continue to brighten. These changes are gradual, but they define the long-term fate of Earth. Long before the Sun exhausts its fuel, Earth will become uninhabitable due to increased solar output. Oceans will evaporate. Atmospheres will thin. Life will be forced to adapt or disappear. This future is distant, but it illustrates a deeper truth. The Sun is not static. It is evolving, and Earth's fate is tied to that evolution. In the shorter term, the Sun controls Earth's space environment. Solar wind shapes the magnetosphere. Solar radiation influences atmospheric chemistry. Solar storms threaten technology. Humanity has built systems that assume stability in this environment. Communication networks, navigation systems, energy infrastructure, all depend on predictable conditions in space. The Sun does not guarantee predictability. When solar activity increases, Earth's magnetosphere absorbs energy and redistributes it. Auroras brighten. Radiation levels rise. Electrical currents flow where none were intended. Most of the time, this is manageable. But extreme events expose dependence. A powerful solar storm does not need to destroy civilization to disrupt it. Temporary outages, satellite failures, and communication disruptions can cascade through interconnected systems. Modern society is efficient. Efficiency reduces redundancy. Reduced redundancy increases vulnerability. This is not a flaw of design. It is a trade-off. The Sun tests that trade-off. The Sun also controls access to space. Human exploration beyond Earth's magnetic shield exposes astronauts to radiation. Solar storms can deliver dangerous doses in short periods. Predicting and mitigating these risks is essential for future missions. Plans to return to the Moon, to establish permanent habitats, or to journey to Mars depend on understanding solar behavior. The Sun becomes not just a background star, but a factor in mission planning and survival. This dependence forces a change in perspective. The Sun is no longer something we simply observe. It is something we must coexist with consciously. This coexistence requires humility. The sun does not adapt to us. We adapt to it. Recognizing this does not diminish human achievement. It contextualizes it. We have extended our reach into space, but we remain bound to the dynamics of a star. The sun's control over our fate is not absolute in the dramatic sense. It will not suddenly extinguish life tomorrow. But it defines constraints. It sets boundaries. It shapes possibilities. Understanding those constraints is part of maturity as a technological species. This realization reframes the idea that the sun is hiding something. What it hides is not a threat waiting to emerge, but complexity that demands respect. The sun operates on timescales that exceed human planning horizons. Its cycles unfold over decades. Its evolution spans billions of years. Human systems operate on years or less. Bridging this gap requires foresight. Space weather forecasting is one attempt to bridge it. Climate modeling is another. Long-term planning for infrastructure resilience is a third. All depend on understanding the sun. The sun has always controlled Earth's environment. The difference now is awareness. We can measure, model, and anticipate to some extent. That knowledge creates responsibility. Ignoring solar influence is no longer an option. The sun also serves as a reminder of scale. Human civilization feels immense from within. From a cosmic perspective, it exists on the surface of a small planet orbiting an ordinary star. That star determines whether conditions remain favorable. This perspective is not meant to diminish human significance. It is meant to ground it. The sun's control is not domination. It is relationship. A relationship defined by energy, gravity, and time. The illusion of safety. The sun feels safe because it has always been there. Every generation that has ever lived on Earth has known the same star in the sky. It rose in the morning. It set in the evening. It followed patterns that felt eternal. Civilizations rose and fell beneath its light. And the sun remained unchanged. At least, unchanged to human eyes. This familiarity creates comfort. Comfort creates assumption. And assumption creates illusion. The illusion is that the sun is harmless because it is familiar. In reality, familiarity does not equal simplicity. It does not equal predictability. And it does not equal control. The sun is powerful beyond intuition. Its calm appearance hides processes that release energies far beyond anything humanity can produce. The only reason this power feels benign is distance and timing. Earth sits far enough away to receive warmth without incineration. Most solar outbursts miss us or weaken before they arrive. This balance is not guaranteed by design. It is coincidence. The sun does not adjust itself to protect Earth. It follows physical laws indifferent to outcomes on a small rocky planet. Earth survives because conditions happen to allow it, not because safety is assured. This truth is easy to forget because danger is rare. Human psychology is shaped by recent experience. When something behaves predictably for long enough, it becomes background. We stop noticing it. We stop questioning it. The sun has benefited from this bias for millennia. We remember eclipses. We remember droughts. We remember storms. But we forget the star behind them. The sun's rare extremes are separated by centuries or millennia. They fall outside institutional memory. They do not influence planning. They are treated as anomalies rather than features of the system. This is the illusion of safety. Modern technology amplifies this illusion. Our systems work well most of the time. Satellites orbit smoothly. Power flows uninterrupted. Communication is instant. These successes reinforce the belief that the environment is stable. But stability is conditional. It depends on the sun behaving within expected bounds. The moment it does not, fragility becomes visible. A single powerful solar storm could disrupt multiple systems simultaneously. Communication, navigation, power distribution, and satellite operations are interconnected. Failure in one area cascades into others. This interdependence magnifies impact. The sun does not need to act maliciously to expose this fragility. It only needs to act differently than expected. The illusion of safety also affects scientific understanding. When systems appear stable, anomalies are dismissed more easily. Unexpected observations are treated as noise. Models are tuned to fit common behavior. Rare events challenge these models. The sun's history shows that rare events occur: tree rings, ice cores, and historical records confirm this. The absence of recent extremes does not mean absence of possibility. It means absence of recent experience. The illusion of safety that also shapes public perception. The sun is rarely seen as a threat. When solar storms are discussed, they are framed as curiosities rather than risks. This framing influences preparedness. Preparedness requires acknowledgement of uncertainty. Uncertainty disrupts comfort. The sun is not dangerous in the everyday sense, but it is not safe in the absolute sense either. It operates within a range of behavior that includes extremes. Recognizing this does not mean fearing the sun. It means respecting it. The illusion of safety also hides a deeper truth. Earth itself is protected by layers of coincidence. A magnetic field strong enough to deflect radiation. An atmosphere thick enough to absorb energy. A distance from the sun that allows liquid water. These protections are effective, but not invincible. Solar storms test them. Over geological time, Earth's magnetic field has weakened and strengthened. Its atmosphere has changed. Solar output has increased. Life adapted because changes were slow. Technology adapts less easily. The sun does not target human systems, but it reveals their limits. The illusion of safety is therefore not about danger, but about perspective. It is the belief that familiarity equals understanding, and understanding equals control. The sun challenges all three. We are familiar with it. We do not fully understand it. We do not control it. Accepting this reality shifts focus from prediction to resilience. Instead of assuming safety, we design systems that can tolerate disruption. Instead of expecting stability, we plan for variability. This approach mirrors how societies adapt to other natural forces. Earthquakes cannot be prevented, but buildings can be reinforced. Storms cannot be stopped, but warnings can be issued. The sun belongs in this category. It is not an anomaly. It is a force. For centuries, the sun was worshipped. Later, it was reduced to equations. Now, it occupies a more complex role, understood enough to be useful, mysterious enough to demand respect. The illusion of safety dissolves when we acknowledge that understanding is incomplete. This acknowledgement does not weaken science. It strengthens it. It encourages vigilance. It encourages humility. It encourages preparation, living beside an unfinished mystery. Every night, when the sun disappears beyond the horizon, darkness falls, and for a while, it feels distant, as if its influence has paused. But even in the dark, the sun is still there. Its gravity holds Earth in orbit. Its energy lingers in the warmth of oceans and air. Its magnetic reach extends far beyond sight. The sun never truly leaves us. By the end of this journey, one truth becomes clear. The sun is not hiding a single secret waiting to be uncovered. It is hiding depth, layers of complexity that resist complete understanding. It is hiding processes that unfold slowly, quietly, and sometimes unpredictably. This does not make the sun dangerous. It makes it honest. Nature does not promise simplicity. It does not guarantee predictability. It operates according to rules that interact in ways often too complex for certainty. The sun is a reminder of that reality, placed impossibly close to us. For thousands of years, humanity looked at the sun with reverence. Later, with confidence. Now, with a mixture of understanding and humility. We know more about the sun than any generation before us. And yet, we know enough to recognize how much remains unknown. This is not failure. It is progress. To understand something fully is not always possible. To understand it well enough to live beside it wisely is the true goal. The sun does not need to be conquered, solved, or controlled. It needs to be respected. The sun gives life freely. It shapes worlds quietly. It reminds us that even the most familiar forces can be deeper than they appear. We live beside a star that has burned for billions of years before us and will burn billions of years after we are gone. For a brief moment in that vast timeline, we observe it, study it, and try to understand our place beneath its light. Perhaps that is what the sun is truly hiding. Not danger, not mystery, but perspective. A reminder that knowledge grows slowly, that certainty is rare, and that coexistence with powerful forces requires humility, patience, and care. The sun will rise again tomorrow. It always does.